Cecil Powell's 1950 Nobel Prize in Physics recognized his groundbreaking work in developing a photographic method for studying nuclear processes. This methodology, first successfully applied to the investigation of cosmic rays, revolutionized particle physics by providing a visual means of observing the tracks of subatomic particles, leading to the discovery of the pion and other mesons. Powell's work stands as a pivotal moment in the shift from observational cosmic ray physics to controlled experiments in particle accelerators. The intellectual landscape preceding Powell's work comprised a complex interplay of theoretical predictions and experimental observations. In the 1930s, Heike Yukawa proposed the existence of a meson, a particle mediating the strong nuclear force responsible for binding protons and neutrons within the atomic nucleus. Yukawa's theoretical calculations predicted a mass for this particle intermediate between that of the electron and the proton. Observations of cosmic rays revealed energetic particles capable of penetrating considerable amounts of matter, initially believed to be Yukawa's meson. However, subsequent experiments by Carl Anderson and Seth Neddermeyer identified a particle with a similar mass, but whose interactions with matter were far weaker than Yukawa's theory predicted. This particle became known as the muon, leaving the identity of Yukawa's force-carrying meson an open question. Powell's innovation involved utilizing specialized photographic emulsions to record the passage of charged particles. These emulsions, thicker and more sensitive than conventional photographic film, contained silver halide crystals that, upon ionization by a traversing particle, would leave a latent image. After development, this image revealed the track of the particle, providing information about its charge, momentum, and range. Crucially, Powell's team pioneered techniques to stack multiple layers of these emulsions, creating a three-dimensional record of particle interactions. This allowed for the observation of rare events and the precise measurement of particle trajectories. The experimental setup involved exposing these stacks of photographic emulsions at high altitudes, typically in mountain regions or via balloon flights, ensuring the capture of cosmic rays before they interacted with the atmosphere. Upon retrieval, the emulsions underwent meticulous development and microscopic examination. Each track was painstakingly traced through the emulsion layers, enabling the reconstruction of particle paths and the identification of interactions. This process required meticulous attention to detail, as the tracks were often faint and obscured by background. The direct application of Powell's method led to the unequivocal identification of the pion in 1947. Observations revealed instances where a heavier particle decayed into a lighter particle, identified as the muon. The decay occurred with a characteristic range, indicating a two-body decay process. Careful measurements of the particle masses and energies confirmed that the heavier particle possessed the properties predicted by Yukawa for his meson. This particle, a pion, interacted strongly with nuclei, differentiating it from the weakly interacting muon. The discovery provided compelling evidence for Yukawa's theory of the strong nuclear force and resolved the puzzle of the cosmic ray meson. The impact of Powell's work extended far beyond the identification of the pion. The photographic emulsion technique proved invaluable in discovering additional mesons and hyperons, expanding the catalogue of elementary particles. Researchers utilized the method to study particle interactions at ever higher energies, revealing the complex structure of matter at the subatomic level. The technique also influenced the development of other particle detectors, such as bubble chambers and spark chambers, which build upon the principle of visualizing particle tracks. Furthermore, Powell's approach influenced the direction of particle physics research. The success of the cosmic ray experiments using photographic emulsions underscored the importance of controlled laboratory experiments. Particle accelerators, capable of producing high-energy beams of particles, became the primary tool for investigating the fundamental constituents of matter. This shift from passive observation of cosmic rays to active manipulation of particles and accelerators marked a new era in particle physics. The reception of Powell's work was overwhelmingly positive. The discovery of the pion filled a significant gap in the understanding of nuclear forces and validated Yukawa's theoretical framework. The meticulous experimental techniques and the clarity of the results garnered widespread acclaim from the scientific community. The Nobel Prize in Physics cemented Powell's legacy as one of the pioneers of particle physics. Some critiques did arise, however. The photographic emulsion technique, while powerful, possessed inherent limitations. The analysis of the emulsions was time-consuming and labor-intensive. The limited volume of the emulsions restricted the number of events that could be observed. Furthermore, the technique was primarily sensitive to charged particles, making it difficult to detect neutral particles directly. These limitations spurred the development of alternative detection methods, that offered improved efficiency and greater versatility. Powell's work received direct influence from several precursors, building of course on Yukawa's theoretical predictions of a force-carrying meson. Also significant were the earlier works of Marietta Blau and Hertha Weinbacher. They pioneered the use of photographic emulsions in cosmic ray research, developed techniques for processing and analyzing the emulsions, and made initial observations of particle tracks. Powell's group built upon their methods, refining the emulsions and developing the stacking technique that proved crucial for the pion discovery. Powell's work directly influenced numerous subsequent researchers and discoveries. Donald Perkins, a member of Powell's Bristol group, continued to refine the photographic emulsion technique and made significant contributions to the study of cosmic rays. Cesar Lertes, another member of the team, played a crucial role in the pion discovery and later became a leading figure in Brazilian physics. Theoretical physicists such as Shinichiro Tominaga, Julian Schwinger, and Richard Feynman directly built off of concepts to develop quantum electrodynamics, integrating Yukawa's ideas of meson exchange forces into quantum field theory. The enduring legacy of Cecil Powell's work lies in its profound impact on the field of particle physics. His development of the photographic emulsion technique provided a visual window into the subatomic world, revealing the existence of new particles and paving the way for a deeper understanding of the fundamental forces of nature. That this window was created on a foundation of painstaking, meticulous effort and analysis stands as a testament to the power of ingenuity and dedication in scientific inquiry. The shift from cosmic ray observation to accelerator-based experiments, informed directly by his research, represents a fundamental transformation in the methodology of particle physics. Powell's contributions continue to resonate in modern particle physics research, reminding us of the power of visual observation and the importance of bridging theory and experiment. His work offered the world its first clear image of what holds the universe together, even as the world held its breath in a post-war era, a truly remarkable feat.